Good morning and welcome once again to National Science Week 2020 here at the Queen Victoria Museum and Art Gallery in Launceston, Tasmania. I'm Martin George, and joining me on Skype this morning is Tasmanian scientist Dr. Elise Allender, a research fellow in the School of Earth and Environmental Sciences at the University of St Andrews in Scotland. Today, in the last of our Science Week live streams for 2020, we're going to be talking about Europe's next Mars mission to be launched in 2022 in collaboration with Russia. And Dr. Allender is performing key work on this mission, and we'll hear about that in a few minutes. But first of all, a good morning to you, Elise, and thank you so much for being up at just after 1 o'clock in the morning in Scotland. So we'll hear from you very shortly. How are things over there at the moment?
Things are great, even though we're kind of just coming out of lockdown. Everything's going fine. So
that's good to hear. We'll be back with you in a few minutes. Now, remember everyone that you can ask your questions online, and at around about 10:30, that'll be 1:30 in the morning for Elise, we'll go through a few of those questions and endeavour to answer as many as possible. Before we do that, a bit of a background about Mars. Now, a few days ago, we were talking about what's visible in the night sky, and Chris Harkless and I mentioned that you can see Mars in the late evening sky at the moment. But let's take a look at a few more pictures of Mars and some of the research that's been done over the years, some of the spacecraft that have been there. So we'll switch through now to some images here. We started looking at Mars in the 17th century, not very long after the telescope began. Looking at Mars telescopically, that is of course. People have been watching it for thousands of years. But one of the key periods was the 19th century, when telescopes were getting better and better. And Giovanni Schiaparelli at the Brera Observatory in Milano in Italy was observing Mars with this wonderful old refractor telescope. And at that stage, he drew some very intricate drawings of Mars with lines, very fine lines across the surface that he called canali, meaning channels. Unfortunately, people thought he meant canals that were built by intelligent creatures on Mars. We now know that they don't exist and they were purely optical illusions. But Mars has remained fascinating for us, and the very first time we saw Mars close up from a spacecraft was when the Mariner 4 spacecraft flew past in 1965. It returned about 22 images, I think, from memory, and it showed Mars to be a crater-covered world. We certainly had our very, very first views. We hadn't seen anything like this before, and so some of the views were, all of these views were really, really exciting. That was in 1965, but since then, we've had many spacecraft that have been to Mars. This particular one we're seeing now is the Mars Global Surveyor, which operated for about 7 years from 1999 in orbit around Mars. We've seen all sorts of wonderful images of the surface from these spacecraft, including dust storms. Mars has some amazing dust storms, for example, and I can remember way back in 1971 when Mars was close to Earth, and I was looking forward to some great views through my telescope, and unfortunately it was just a blank disk because of all the dust. And we can see here what can actually happen. This picture was taken from a spacecraft on the surface, and we can scarcely see through the dust. Other missions have included the Mars Odyssey spacecraft, but what about landings on Mars? And certainly we're going to be talking about that with Elise very shortly, but it's not so well known that before the United States had a lander on the surface, the very first one to successfully land there was a Soviet craft called Mars 3. And we can see here a full-scale model of this in the Museum of Cosmonautics in Moscow. It got to the surface, started transmitting after 90 seconds. 21 seconds later, it went dead. And unfortunately, we didn't get any photographs from the surface. But as I've mentioned, the United States landed a spacecraft there a few years later. This was Viking 1, one of the most exciting pictures of the 70s to come back from space. And at the moment, we have a couple of craft on the surface. The Curiosity rover is certainly the more well-known of the two. The other one is called the InSight lander, but Curiosity has been sending back some amazing information about Mars for us as well. And in recent times, we've seen 3 launches toward Mars. The United Arab Emirates have sent up their mission called HOPE, which is going to tell us more about the Martian atmosphere and climate. We've had a Chinese launch. They're sending up an orbiter and a rover. And most recently, NASA's Perseverance rover, which is carrying the first helicopter to Mars. And that's going to be very, very exciting. Those missions will arrive there early next year. And now to hear about Europe's next mission, which would have gone up this year, but for a few problems, and I'm sure Elise will mention why that hasn't happened, but we're certainly looking forward to it now becoming ExoMars 2022 instead of ExoMars 2020. I'll now hand over to Elise, and we'll take a look at, we'll have a listen to what Elise has to say about her wonderful research. So over to you, Elise.
Thanks, Martin. I'm just going to attempt to share my screen with you all. So if you just give me 1 second.
Yeah.
How's that?
Looks pretty good.
So, hello everyone, I'm Elise. And as Martin said, I'm a research fellow at the University of St Andrews in Scotland. And for the past 3 years, I've also been a member of the Pancam science team. So Pancam is an instrument on board the ExoMars rover. And today I'm just going to tell you a little bit about the ExoMars mission and talk about the landing site and why it was chosen. Talk a little bit about the rover and the instruments, a little bit about my work and where it's taken me. And also one of those places is to Australia. So I'll show you some pictures from Western Australia. But first, just related to what Martin was saying, I just want to show you this slide of Mars' surface, and it contains the positions of some of the missions he was just talking about. So you can see this is an elevation map. So everywhere that's red on this map is quite high and mountainous, and everywhere that is low is shown in blue, blue screens essentially. So you can see. In case you're not familiar with this kind of map, I'll just quickly show you one of Earth. So this is what Earth looks like using the same kind of elevation scale. Mars itself is about half the size of Earth, and you can see that most of the landed missions that have gone there have focused on the mid-latitudes of the planet. So that's centering on this region between the 2 hemispheres. So the southern, heavily cratered, highly elevated terrain of the southern hemisphere, and the smoother, much younger looking terrain of the northern hemisphere. So it's thought that the northern hemisphere used to have a global sea. And so these missions have landed in the region between the hemispheres where you can see features like you would see on Earth, where that might have been carved by water flowing down some channels. Another reason why all these missions have landed in the mid-latitudes is because they get a lot of sunlight throughout the year, constant sunlight, which minimizes temperature fluctuations and things like that to the instruments. Also, you want to pick a landing site that has a low elevation because a lot of these missions are landed with parachutes, and you'd like to maximize the amount of time you have landing your craft, just really slow it down coming through the atmosphere, as slow as it can possibly get before it lands to minimize the risk for the spacecraft. And finally, as Martin also mentioned, these regions, you can see the hashed regions contain a lot of dust. And if you want to be looking for particular outcrops of interest to view with a rover or a lander, then you don't want them to be covered in dust. You want to be able to see them correctly. So all of these mid-latitudes are good places to put a rover down. And so ExoMars is going to Oxyoplanum, which you can kind of see if you can see my mouse here. And I'm just going to zoom in and show you some of the terrain in the next couple of slides. So here I've zoomed in the landing ellipse. So this is a 100-kilometer region where ExoMars has the highest probability of landing. You can see it's surrounded by kind of a low plains area, and you can see an outflow channel coming up from the bottom of my screen where a volume, for example, of water has really pushed through and carved out, pushing through these little islands that have not eroded due to whatever material has come through. Another slightly closer view of Oxyplanet, and the most high-resolution image of all. So just to give you a sense of scale for this landing ellipse, if you're in Launceston, it's the same kind of distance as driving from Launceston to Devonport, contained within this ellipse. And if you're in Hobart today, then it's kind of like driving to Campbelltown in size. So the rover could land anywhere between this kind of distance. And so you can see here at the bottom of the landing ellipse, the ending of one of these outflow channels. So material would be carried down this channel and deposited into this kind of river delta fan at the bottom. And we also know from orbital imagery that this landing ellipse contains a lot of clay material. So clays can only form in the presence of water. And the most important aspect of finding life is that life requires water. So this is obviously a wonderful place to situate a landing mission. So we would also hope that evidence of life, microbial life, might be preserved in fine-grained sediments in the soils within this ellipse. So here is the rover itself. This is ExoMars. It's also known as Rosalind Franklin. So it was named after a British chemist whose work was central to understanding the structure of DNA, because it is a life detection mission. So its two main goals are to search for signs of life, past and present, on Mars, and also to really understand the history of water on the planet as well, on the surface and the subsurface. So ExoMars has 9 instruments on board, and the one that I'm going to talk about most is Pancam. So that's basically the eyes of the rover up here on the top of the mast. Now, this is a little video, so I hope it's going to work. But essentially, when ExoMars lands within the landing ellipse, it's going to use Pancam to have a look at its surroundings and try and get an idea of what kind of geology is surrounding the rover. And then it'll work with instruments called spectrometers, which are on board, to really get detailed observations about things that it sees of interest within its images. And if it finds a target, it would like to really investigate with the instruments that are, the rest of the instruments that are on board the rover. It's going to, this big black box on the front is a drill. So if I play this, hopefully you'll see it turn. So what it's going to do is take a drill, and the drill goes 2 meters below the surface and comes up containing a sample core. So it'll be doing that right now. When the core goes into the drill, it's imaged by some spectrometers that are inside the drill, and it spits out the sample that it's taken into the sample tray, and it takes the sample inside the rover where it's analysed by a mass spectrometer, which looks for organic molecules, basically. So it can take on board, I believe it's 21 samples for analysis. And just for your information, this is how large the rover is. This is actually Rosalind Franklin's niece standing next to it, so that's quite nice. So what I'm going to mainly talk about with respect to my work is this instrument Pancam, which I've mentioned is the eyes of the rover. So Pancam itself is made up of 3 cameras. The 2 on the very edges here are the left and right cameras, and this one here is a high resolution camera. But these cameras are stereo, so they're set apart on what's called an optical bench, so they can create 3D color images as well. So essentially, my work for the past 3 years has been taking a replica instrument of Pancam, which you see here. This is in Iceland. And I take it to locations on Earth that are called Mars analogues. So these analogues possess characteristics that are similar to those we might expect to find on Earth. And so
Elise, if I could just interrupt for a second there. It looks like there's a great picture in the upper right of that screen. I think the feed from my end is blocking part of that. Maybe you could drag me away. Oh, lovely. Thank you. Okay, sorry, do go ahead.
Sorry, I've ruined my screen now.
That looks great. Thank you.
No. Oh. Okay.
You're right now?
Okay, I'm right. So
great, thank you.
the two cameras that you see here that I've talked about, which make up Pancam, each contain a filter wheel with 11 slots for filters. So you can see the filters down here in the bottom corner. There's red, green, and blue ones in each camera. And then there's 6 geology filters. So these filters let in light at different portions of the visible and near infrared spectrum. So not only can Pancam take color images, but it can take multispectral images, including wavelengths that we can't see with our eyes. Another thing that this means is that each pixel in a Pancam image essentially contains, or can contain, 12 different points of information, and these about where light is reflected or absorbed. And so what this will tells me is about the composition of the material that's being observed in an image. I'll show you some examples in just a sec. So these are some of the places that I've taken the replicas to. In the top left is some channel features in Utah, so it looks quite Mars-like. Just next to this field site is the Mars Desert Research Station, where they send people to live out in a desert habitat and pretend to be astronauts. So the channel features that I was imaging, you can see throughout the image. In the bottom left, you can hopefully see a very large outcrop, which is interspersed with gypsum veins, which have been observed on Mars by Curiosity as well. So I was testing how Pancam will observe these features to the best of its ability. And down on the right, I'm standing on top of one of these channel features in the Utah image. So we imaged up and down the sides to get an idea of the stratigraphy of these channels. And I should just mention, at Oxyoplanum, at the landing site, the topography is not anywhere near as sharp as this. So we are expecting layered deposits, but they are kind of on a centimetre scale. It's a very, very flat landing site. So here is an example of when I took the replicas to Iceland. So this is a fumarole, which is essentially a big smoke pot, and all of the ground in this area is basaltic, volcanic and basaltic, just as it is on Mars. So at this site, I was looking at how the basalt has been altered using this very acidic geothermal alteration process. So here is what Pancam sees. This is one of those fumaroles, but it's gone extinct, so it's not active anymore. This is what you see as a mosaic of traditional Pancam images. And I'm just going to zoom in here and show you that each pixel in this image contains one of these, what probably look like squiggly lines. So each of these lines is the response, how much light is reflected from each of those 12 geology filters that I showed you before. So by looking at the shapes that all of these of the reflectance and absorption of light in each pixel, we can get an idea of what the soil, what materials the soil contains, what minerals are in it, and things like that. And on the right-hand side, there's additional information from the ICEM instrument. So that's a Russian spectrometer, which is co-located with Pancam, which also tells you if a mineral in the soil, for example, has been hydrated or formed in the presence of water. So these dips in the spectrum are where it is absorbing light, which is indicative of the presence of water. Another method of getting information from Pancam images that I use is to create false color combinations. So this is another way of representing those previously squiggly lines. so that you can get information about a scene all in one go instead of analysing hundreds of those individual plots. So you can see in the top left one here, this is representing the slope from blue, which is 438 nanometers of light, to red, which is around 671. So if there's a high slope, for example, from here to here, a pixel will show up red in this image. So essentially my job is to easily reduce all of this spectral data into manageable information so that scientists can really look for targets that really stand out in these images as really interesting targets to analyze with the drill and with other instruments. One final way of reducing data from Pancam is when you look at an image on a computer, you can create what's called a true color image. So this is when you have red, green, and blue, some combination of red, green, and blue channels, and you assign red light, which has a wavelength of 640 nanometers, to red channel, green light, which has 540 nanometer wavelength to the green channel, and blue to the blue channel. And so all the colors look correct. The correct wavelengths are assigned to their respective channels. You can also switch these around and assign infrared wavelengths to the red, green, and blue channels. So in this image, you can hopefully see there's a kind of got a purple tinge throughout this piece of basalt. And things that are purple, so essentially a combination of a mixture of blue and red, these things have a high reflectance. They reflect light at 1,000 nanometers and at 740. And this tells you that they would have kind of a spectral shape like this, a high reflectance around 740, a dip, and then a high reflectance around 1,000 nanometers. So, I'll talk about this in a moment. Essentially, this mauvey coloured map is representative of a mineral called hematite, which forms in combination, grey hematite forms in combination with water, and it's been found on Mars by Curiosity also. So as well as taking the replicas out to these Mars analog locations, I've also taken part in the ExoMars-like field trials, which is basically a field test for the operations team in which the rover and all the instruments, or a replica of the rover, is sent out to a Mars analog location like Tabernas in Spain or to the Atacama Desert in Chile, and myself and the other members of the instrument teams are based in Oxford in the UK. And each day we make a work plan for tasks for the rover to execute. And overnight, due to the time differences, the rover undertakes the tasks that we sent it and sends us back the imagery that we asked for. And we do the same thing again every day. It's a very high pressure situation, but it's important that all the instrument teams, all of these procedures work very nicely together, because ExoMars, during its mission phase, is going to cost about 10 million euros a day to run. So if you haven't got a work plan sorted out, or you haven't got key targets to image, then it's very much a waste of resources. And finally, this time last year, alongside NASA Mars 2020 scientists and some other ESA scientists working on ExoMars, I was out in the Pilbara. And the Pilbara is actually home to some of the oldest rocks in the world. They're about 3.6 billion years old. And this is quite a nice analogue for Mars, because the rocks in the terrain on Mars that we're looking at are around 4 to 4.5 billion years old. So the very interesting features that we were looking at in the Pilbara were called stromatolites. And stromatolites exist today. This is in Shark Bay in Western Australia. And so these stromatolites are still living. Basically, bacteria create what's called microbial mats. And this is kind of like pond algae. And they thrive in a shallow, warm water environment, which is kind of analogous to what we're looking at the landing site on Mars. And so these bacteria create kind of an algae net. And as the water rises and falls around them, sand and sediments get trapped within these mats, and they kind of accumulate and build over time. And there's fossilized evidence of these in the Pilbara, which represents some of the earliest known life on Earth. So this is what they look like, preserved in the Pilbara. You can kind of see the very small dome-like structures. Here there's some people standing around for scale. And then on this side, there's kind of a cross-section of one of the large domes with some below. So just for scale here, I didn't include a scale, but this white rock over here is about the size of a 50-cent piece, if that helps. Here's another very nice outcrop. This is kind of on its side. So up is coming towards you, and you can see the stromatolites coming out towards the screen. And in cross-section, they have quite distinctive features. So they're kind of a wrinkly, ridgy kind of feature. So if we were to see this on Mars, it would be quite strong evidence for biological formation. Obviously, it wouldn't be absolutely conclusive because there are geological features that can fold and bend like this, but it would be quite nice evidence for life on Mars. So with respect to ExoMars, the new timeline is we're slated for launch, I think the 20th of September, 2022. So the landing should be around the 10th of June. The 10th of June, 2023. The landing ellipse that I showed you before, unfortunately, due to the orbital calculations, is not going to be exactly the same. So there's a lot of geological mapping of a new ellipse being done right now to characterize that terrain from orbit before ExoMars arrives there. So currently the rover is in Turin in Italy, and there's some testing being done in Rome, and additional parachute testing is also going to be done in the coming year, I believe. So this is just a picture of the rover after it underwent environmental testing in Toulouse. So this is where they test in a vacuum, test all the instruments and that they work, thermal shock, test the temperature extremes and things like that. So now it's nicely packed up, not in Toulouse, but in Turin, and where it will remain until the time of its launch. So between now and then, I finished my project with the Pancam replicas. So until then, I'm going to be writing some image analysis software which will produce those colorful images I showed you before in time for scientists to analyze the data as it comes back from Mars. So I'm creating a tool basically to make this process as smooth as possible so that targets can be prioritized for sampling with the rover. And that's all I have. I'd love to take your questions if you have any at the moment.
Okay, well, thank you very much for that, Elise. And I'll just see if we can get your face back on the screen. Perhaps if you turn off your screen sharing now. We've had a question. What is your name? Perhaps it was from somebody who wasn't with us at the start. Just to remind everyone, or people who've just joined us, I'm speaking with Dr. Elise Allende. She is a research fellow at the School of Earth and Environmental Sciences at the University of St Andrews in Scotland. I think Elise is just that's right. Yes, just finishing her screen sharing now. And we had a question also from Sydney. How many rovers are currently on Mars? And do they normally land on the same location? I think you covered that a little bit earlier, but perhaps we could return to that question.
I did cover it a little bit earlier. So they don't land in the same location, but they do often land in that central mid-latitude region. If you have a rover that you want to do polar type studies with, obviously it would be focused more toward the polar regions. But currently, I guess the correct answer is all of the rovers that have ever been to Mars are still on there. But the active ones are Curiosity. Hang on, I can't bring up my map again. But Curiosity. Sorry, I'm wondering if I can share my screen again.
Of course, we did have a few years ago a couple of rovers that lasted for many years, didn't we? The NASA rovers, Spirit and Opportunity. Yeah. Amazing they were. They had a nominal lifetime of about 3 months, and they lasted many, many years. So
yeah, Opportunity only expired. Was it earlier this year or at the end of last year? In a dust storm, I believe.
Wasn't long ago.
No.
Wasn't long ago. Now, actually, Elise, you mentioned dust storms, and I mentioned them earlier on, but we actually had a question by email earlier this week from to the planetarium from someone who knew this was coming up. How do you stop the dust on Mars from getting on the lens or blocking the view or getting stuck in the camera mechanism? What's done about
that? You don't. I have heard that the Curiosity rover, basically they point it downwards during these storms so that the dust doesn't accumulate in the lenses of the camera. But they do. So dust does accumulate, for example, on the solar panels of rovers, and also on the side of the rovers, there's often a little calibration target that we use to correct colours, because colours on Mars appear slightly redder than they do on Earth. So dust really accumulates on these reference colours. And some of the rovers have, the dust is slightly magnetic, so some of the rovers have magnets on the target to try and draw the dust off the colourful pieces of target.
Right.
So some dust mitigation is planned for, but there's not a lot that you can do, really.
No, I suppose if there's a major global dust storm, any spacecraft on the surface would be in quite a bit of trouble, wouldn't it? So, yes, and we've seen that happen before. You mentioned, Elise, about the fact that the rover is going to be looked after. I think you said in Turin, in Italy.
Yes.
That's where it's going to be. But I remember way back to when the Galileo mission was delayed because of the delayed shuttle launches way back over 20 years ago. And it was in storage for a while. And after it was launched, it didn't unfurl its radio antenna properly, and it was put down to the fact that it had been in storage. Now, is there some danger that 2 years of storage is going to adversely affect the rover?
I don't think so. I would say that it would undergo all the same certification, all the same tests that it has pre-launch, especially because at the moment some of the instruments, I believe, have been taken off. A couple of updates need to be done to some of them and a little bit of calibration. So it will undergo more testing again before launch. So it hopefully will minimise the risk of that.
Certainly be well worthwhile, I think. We've had a question from Astro Glenn. Where did you do your studies in Tasmania, and what was your career path?
Oh, so I did my undergrad at UTAS in Hobart, and I did a Bachelor of Surveying. So I was into mapping, and through that I got into remote sensing, which is essentially mapping from orbit. From there, I went to the US and did my PhD in this orbital mapping, and basically made a tool to automatically pull out minerals of interest from very large data sets. So it was kind of like a data mining, machine learning type project. And that kind of gave me the skills to be a research fellow where I am right now. The Pancam team was looking for someone to develop a tool to analyze the mineral data from Pancam. So I was really in the right place at the right time, and I had the right experience. So yeah, but you don't have to. Just to clarify, you don't have to have a solid science background. Involved in the planetary sciences are a lot of people in communications, in outreach, doctors, psychologists who put human space teams together. So there's a lot of fields you can specialize in and still have a career in planetary science.
That's very sound advice, actually, because so many disciplines do come into it, don't they? And with astronomy in general, I think we were saying the other day that many of the sciences all come into astronomy so well. One of the things I was asked only the other day, actually, on a radio program, was how people work out what these things are made of, what is on the surface of the planets and how they can analyze them. And you've shown that to us very, very well. I was amazed at the actual number of different wavelengths that you're able to look at. It's really quite a wonderful instrument. And of course, we've been able to realize that we can do this over the past 100 years or more than that, in fact, right back to the middle of the 19th century when Kirchhoff and Bunsen were doing their famous experiments, working out spectra and so on. So we've come to a point where we're very advanced now with what we do, and you're certainly putting this to absolutely wonderful use. I'd like to change the subject back to the cost of the mission. You mentioned 10 million euros a day. Now, that isn't taking into account the cost of building the spacecraft and launching it. That is ongoing, is it? The ongoing cost.
Well, that is taking into account the cost so far. So far it's cost about 2 billion euros. So if you divide that over the mission time, it works out to about 10 million a day. But then on top of that, there's obviously staff costs and all of that sort of thing as well.
Yes. So it all goes together to add up to quite a sum.
Very hefty sum.
Look, in my view, what we're learning is certainly well worth that kind of money because we're learning not just about Mars, but about planets in general, about the history of formation of the solar system, the possibility of that life could once have existed on the surface of Mars. There's just so much that we're actually learning. So when you think about the cost per person in Europe, it's actually, I think it's very good value. You are collaborating, of course, with Russia on this mission. So how are things going there at the moment in terms of the preparation for housing the spacecraft, hibernating it for a while? And are the Russian scientists also having to keep stuff on hold? And what are they doing about that?
They are keeping stuff on hold. I think they have. So one of their instruments on the rover is ICEM. It was also on the optical bench alongside Pancam. I think that has been taken off for a little bit of extra calibration. So they'll be working on that at the moment. They also have instruments. So ExoMars, when it lands, it's on a surface platform which has additional instruments on it, and they have some of those as well. So the nice thing about ExoMars is it actually involves so many nations. Everyone has their own little piece of the puzzle to work on. So everyone's going to be quite busy.
And with so many of these space missions, of course, Elise, people from all over the world often join in, scientists from various different countries with many different projects and so on. And I think it's a wonderful collaborative effort. We have another question about the camera, Elise. Are you able to tell us what the camera resolution is in pixel size and also the field of view? Can you tell us a bit more of the details about that?
So the field of view of Pancam is about 34 degrees, but the pixel size depends on how far away from whatever you're looking at is. But you can get up to quite a high resolution. So Pancam can image grain sizes as well, which is something that we're interested in. So you can image grain size fairly well with the two main cameras, but with the high resolution camera, which was mounted in between them there, that's really for studying rock textures and rock grains as well. So the resolution can be quite fine on that.
Oh, excellent. Yes. And actually, another question from me about the camera. I was talking earlier with you about the possibility of dust on the camera and so on. But in terms of the landing on Mars, what is there to protect the camera system during the landing? Do you, for example, and we've often asked this at the planetarium, do you use lens caps that need removing or anything like that?
You know, I actually have no idea. I don't think there'd be a lens cap because there's no mechanism to remove it.
Right.
Honestly, I couldn't give you a definitive answer. I'm sorry about that. I'm not sure about how they store it.
No, that's okay. I asked the question because many people remember the story of a Russian Venus lander many years ago. that did have a lens cap on the camera, and the lens cap popped off and landed on the ground exactly where the robotic arm was due to land on the surface and sample it. So we certainly wouldn't want anything like that to happen. But I just wondered if that was something that was done on the spacecraft today. You might have already mentioned this, but what's the actual planned nominal lifetime of the rover?
So the science mission phase is 200 days of critical mission science. So anything after that is bonus. But I mean, rovers can be quite long-lived, especially those with solar panels. So we're not, as long as there is sunlight, we're going to have a little bit of power to play with. So hopefully we'll see several years out of the rover.
Indeed. I have another question that's come in also about the camera. The question is, yes, I should have said, what is the sensor size? Is it 1024? How many pixels by how many pixels? Do you know? Yes.
It is. It's 1024 by 1024.
Okay, right. That answers
so
that.
So the image size is 2 meg when it comes back.
Right, 2 meg. And of course, to some people, 2 meg might not sound all that much, really, because we're used to digital SLRs that have 24 megapixel or 36 megapixel sensors. But 2 megapixels is obviously enough for what you're doing, right?
It is enough. But the other thing is, when we're doing the field trials that I spoke about, we have a specific data volume that we have to keep to. So actually, I mentioned that there are 12 geology filters in Pancam. There's not going to be very many occasions where we have enough data to use all of them. So we'll really have to select 3 default ones to go with, just to minimize the amount of space data that is shared across the whole rover. The other instruments need their data too. So.
Right, of course. So it's a matter of sharing it around, isn't it? Is there any possibility of camera images from the craft as it's coming into land?
I don't think so. They do flight checks as it's on its way and such. So they cycle the instruments off and on to check that they're all okay. But I don't think there's imagery as it's coming in, but I'm not 100% sure about that.
Okay, because I know that there are some other craft that actually have imaging systems that help the craft learn where to land or decide where to land, which of course would have to be done locally and autonomously by the craft. And I think the Perseverance rover might be doing that to avoid landing on a boulder or something like that. But I suppose there's always that risk when you land on Mars. You might have a boulder and it tips the craft up or something like that. So
it's extremely risky. The whole thing is extremely risky.
Indeed. We don't have any more questions at the moment, Elise, and we are about to finish our session. So thank you so much for joining us here at the Queen Victoria Museum and Art Gallery this morning. It's so wonderful to speak to a Tasmanian scientist who's working on such an important mission. We've very much enjoyed your company. And of course, I'll ask now, perhaps for future science weeks, you might like to come back and give us a bit of an update on what's happening. That would be really great. And of course, everyone, science is around us all the time. And following this year's theme, here we've seen this week how much there is to know about the oceans and the estuaries, the tides, the blue economy, but also how we're reaching out to other worlds with our wonderful space missions, and also how everyone can enjoy their view of the night sky, especially if you're out there in the country when you're well away from the city lights. And as a reminder, late in the evening at the moment, you can see Mars. It's coming up late evening, and by around 11 o'clock, it should be clear of the trees or hills over to the east, a very obvious reddish-orange point of light. And as you look at Mars tonight, you might like to think again about how we're making such a great effort to study the red planet. Elise, thank you once again for joining us. I wish you all the best with ExoMars 2022. I know it's nearly 2 o'clock in the morning where you are in Scotland. It's so kind of you to have given up your sleep for us here at Science Week at QV Mag. So thank you very much. I'll say goodbye to you. Cheerio.
Cheerio. Thank you for having me.
It's been a great pleasure, and goodbye to everyone who's been watching all of our live streams this week, not just this one. We've had many really great chats here at QV Mag. Join us again for Science Week next year, but don't forget, here at QV Mag in Launceston, there's plenty to see all the time, so do come along and visit us. I'll say bye-bye for now. All the best, everyone.